Hello everyone, Mr. Fritz here. In this video we're going to talk about dot products and angles between vectors. Let's dive right into this. First off, we want to talk about the angle between vectors. For example, I have a vector A, I have a vector B, and I'm curious about the angle formed between them. We're going to follow this process that we're going to talk about right now. And think about why we would need to do something like this. I know normally when we combine vectors, we've been adding tip to tail, and we've been subtracting, and we've been adding. It's always been tip to tail, tip to tail, tip to tail, tip to tail, tip to tail. Well, why would we want two vectors emanating from the same point? Well, think about if this is like some sort of an object, and I'm pulling on it in this direction, and then another force is pulling on it in this direction. I'd be curious about what's going on between the vectors, even though they're both coming from the same point. So that's why we might want to learn what the angle is between two vectors. So consider this drawing that we have right here. I have these two vectors, and this blue line is kind of not the resultant because I'm not adding them, but if I were to form a vector between the ends of these two, or the tips of both of these, that's the same thing as vector B minus A. And hopefully that makes sense. If I were to start here, I could travel a negative A direction and then add B to get this. And so there you go. I mean, this is the same thing as B minus A. So the length of this is the magnitude of that vector. We can add to that using the cosine rule. If you remember the cosine rule that says that this side squared is going to equal this side squared plus this side squared minus 2 times AB times the cosine of that theta. And I'm not sure if I'm hiding anything behind this. Nope. So that's your law of cosines. It's just used with these magnitudes of these vectors. Moving further with that, I could take the cosine rule and I can simplify all of this to this blue formula right here. And this does boil down, this line right here does simplify to this with a little bit of algebra, and I would encourage you to see if you can't figure out where that comes from on your own. In fact, if you can prove it to me, maybe I'll even throw you a bonus point. Who knows? But that simplifies to this, and I can find that angle by now solving for the cosine, doing a little bit more algebraic rewriting, and I get the cosine of theta equals A1 B1 plus A2 B2, all divided by the product of the magnitude of vectors A and B. So we can use all of this information to find the angle between these two vectors. Another way that you might see this is with there's another version of this formula I'll show you in just a minute. But right now, remember that the A1 B1 and A2 B2 refers to the x values, A1 B1 and A2 B2 refer to the y values of those vectors. So that's how we can find that angle. So let's talk about why we might want to use or find this angle. And first, we need to talk about something called the dot product, also known as the scalar product. This is an absolute new operation. You've seen addition, you've seen subtraction, you've seen multiplication, you've seen division. This is a new operation for you. So pretty exciting. You didn't know you were going to learn a new operation right now, but you are going to. But before we dive into this whole dot product, scalar product thing, let's consider these weights. So I want you to imagine that you are lifting this 10 kilogram weight and you are holding it by the handle and you're pulling it up. And so in each of these three scenarios, you're just going to be pulling this straight up. Just pretend that those are straight up as you're pulling these. And imagine somebody else has come along and they're like, oh, hey, let me help you. I see that you're carrying that 10 kilogram weight again. And I want you to think about what would happen if somebody grabbed the handle and pulled kind of in this direction. Think about if somebody was walking alongside and said, here, you know what, let me just push this for you. That'll help you lift this weight up. That'll be real helpful. Anything I can do to help. That's scenario number 2. And then scenario number 3 would be somebody is not really your friend and they are pushing down in this direction. Now, really, I hope that you can think through these scenarios and think, well, which one is the most helpful and which one would be the least helpful I could add to that. This one definitely is the most helpful, right? We're kind of pulling, maybe not in the same exact direction, but there is some upward motion going on, which is helping you lift this weight. And it's quite clear that in this scenario, your friend is pushing the weight against you, and your resultant vector between the two is not as productive as just what you alone are doing. So this is like not a good way to carry a weight. Now let's think about this third scenario. What we're doing here is if I drew this really accurately, these forces would kind of be perpendicular to another. One, you are trying to pick up the weight, and your friend is just pushing it in a perpendicular direction. Are you going to feel like that's going to make the lifting any easier? Probably not, or definitely not. Right? This force that's moving horizontally has nothing to do with the force that's moving vertically. So I want you to think about that, how vectors kind of affect or magnify or oppose or not affect each other. And that's kind of what we're taking away with these dot products or scalar products. And let's start off by talking about how to find if vectors are perpendicular. So we were able to find that formula before for the angle between two vectors. And I want you to think two vectors are perpendicular if that angle, that theta, is equal to 90 degrees. We have a formula that solves for the cosine of theta. And we know that the cosine of 90 degrees is, unit circle time, is 0. So basically, if you use that formula that we saw before, the cosine of theta equals a1 b1 plus a2 b2 over the product of the magnitudes of these vectors. If this all shakes out to be 0, you have yourself two perpendicular vectors. And that is basically essentially what you're doing when you're finding the dot product. Here's the you're finding the basically the effect that a vector has on another. Is it kind of move? Are the two vectors kind of moving in the same direction? Are they opposing each other? And or are they not affecting each other at all? That's kind of what the dot product tells you. We call this thing a scalar product because it actually just spits out a number. It doesn't spit out a magnitude and direction, just a number. So let's talk about the dot product between these two vectors. If I wanted to find the dot product between A and B, I would write this as vector A dot, and this is kind of a bigger multiplication sign. It's not really the same thing as regular multiplication, so it gets a bigger dot. And this is going to be defined as multiplying, I should just use parentheses, A1 times B1 plus A2 times B2. So essentially what I'm doing here is I'm multiplying my x components together, and I'm going to be multiplying my y components together, and I'm going to basically add that up. So again, it's kind of like how much are your x's affecting one another and how much are your y's affecting one another, and then you're just going to kind of add that up into one number. So this equals a scalar value. And that's how you find the dot product between two vectors. So going back to our formula from before, we can actually change this formula, this numerator of the cosine of theta is actually the dot product, A dot B, over the magnitude of A times the magnitude of B. So you might see this equation in either form, and they both mean the same thing. You can use this to find the angle between two vectors, and that's going to show you whether or not these things are perpendicular. So if this whole thing ever simplifies out to 0, then you have yourself two perpendicular vectors. Let's see some examples of what we can do with this. We want to find the dot product between vectors p and q given this information. Well, p dot q is going to equal 2 times 1, that's the product of my x components, plus 3 times 4, that's the product of my y components, which is going to equal 2 plus 12, which is equal to 14. That's it. This is a scalar value. It is a scalar product because it just spits out a number. There's no bearing or direction to this. This is just a number that kind of quantifies kind of how much these vectors are impacting one another. So simple as that. I want you to try this problem. I've got 3 vectors all in component form, and I want you to try A, B, and C. See if you can't find what the scalar product is of all of these things. You might notice that in letter C, you have to do a little bit before you take the dot product, but I think you can figure this one out. So pause the video and give this one a shot. All right, and here are my 3 answers for these 3 problems. Let's try another example here. We want to find P dot Q, but this time we're not given the components. We're given a magnitude or 2 magnitudes and an angle. So, but if you remember before, we found that if you go back to our slide when we first introduced this equation, I have the dot product is over the magnitude the product of the magnitudes is equal to cosine of theta, I can rearrange this equation to find the dot product like this. P dot Q is going to equal the cosine of theta times the magnitude of P times the magnitude of Q. Or you'll probably more often see this in the other order. Magnitude of P times the magnitude of Q times the cosine of the angle in between them. So this is the same thing as your dot product. So it's another way of doing it. We can find the dot product in component form, we can find the dot product in magnitude form, and as long as we know the angle between them, we should be able to do this. So let's give this a shot. So the magnitude of P is 2, magnitude of Q is 5, and I want to take the cosine of my angle, which is 60 degrees. And luckily we don't need a calculator for this because this is one of our special trig values. This is 10 times the cosine of 60, which is 1/2. So the dot product between vectors P and Q is just 5. So we can find the dot product, reviewing here, we can find the dot product in component form, or we can find the dot product if we're given magnitudes and an angle in between the two vectors. So why don't you give this next example a shot, very similar. Pause the video and resume when you're ready to see the answer. All right, so this is my working out for this problem here. The solution comes out to be -9. All right, let's take a look at the next example here where we're trying to find some value for t if I'm telling you that these two vectors are perpendicular. So, well, if I know that they're perpendicular, I know that the dot product is equal to 0, right? That means that the angle between them should be 90 degrees, and the cosine of 90 degrees is 0. That means that the dot product must equal 0. Okay, so that means that when I take the dot product, P dot Q, that's going to equal 3 times -2 plus t times 1. And I know this whole thing has to equal 0. So I just have a little algebra problem here. This is -6 plus t equals 0. If I solve for t, t equals 6. That's it. And I could check this by plugging 6 back in for t, find the dot product between those two things, and it should come out to be 0. A dot product of 0 kind of means that these vectors have no effect on one another. And if you think about the weight, if I'm pulling and pushing in perpendicular ways, those vectors don't really affect one another, at least not in the direction of their magnitude. So here's another one that I'd like you to try. This one's a little bit trickier, but I think you can do this one as well. I want you to find t, given that these vectors are perpendicular. And we have a lot of t's all over the place. So give this problem a shot and resume when you are ready. All right, so here is my working out for this. Turns out there are 2 values that would work for t. And you can check out my work here. I found the dot product, and it turns out to be a quadratic. You can solve the quadratic by factoring. And I even checked those values of t just to make sure they both work. So hopefully you're able to get that one. Let's take a break here in this video, and then when we come back, we're going to do some more of these examples, just changing things a little bit. So I'll see you in the next video.